Morning, everyone. Before we get into the lecture material today, I just want to make sure that everyone's accessing the course material okay. And what I mean by that is I post the lecture slides well in advance, and so I think right now on D2L I've got up to lecture 9 or 10. Everyone accessing the lecture slides okay if you need to? Course outline should be uploaded. I know there was an issue with the course outline recently, but that should be there now. And quizzes, lecture quizzes, is everyone accessing those okay? Yeah? And the other reminder is I am recording these lectures when things work out for me. I'm hoping to go 35 for 35 this term, but you never know what will happen. But those are also uploaded, so lectures 1 and 2, the videos, the whatever I'm recording on my screen, plus audio is there from the last 2 lectures. And so if anyone ever has issues accessing the videos, and I actually did successfully record the lecture, then please let me know about that, okay? Any questions about anything else before we get going this morning? Okay. So I'd like to kind of come back to this definition of structural engineering because this is a course about structural engineering. And so I kind of like how the different lines of this particular definition complement the structure of this particular course, or maybe I should say I've structured the course in such a way that it lines up well with this definition of structural engineering. And so I presented this the first day, and last time, on Friday, we started talking about structural steel, the material that we mold into shapes that we don't really understand, into shapes we can't really analyze. And so we looked at some wide flange shapes, some WTs, some HSS sections, angles, flat bar, round bar, channel, for example. And those are the shapes, the cross-sectional shapes that we have at our disposal to build with, generally speaking. And so oftentimes we're not coming up with new structural shapes very often. Those shapes exist. There are several different kinds of them. They're tabulated in the handbook, so we know what kind of strength and cross-sectional properties we're working with. And we can just look in the handbook when we need to find that information. Today we're going to be talking about how we take those shapes in certain lengths of sections to actually form a structure that would be the skeleton for a building that's being constructed, mostly to have people inside. And just a reminder, in this course we're talking about buildings, not bridges, and generally not other kinds of structures that wouldn't be classified as buildings. So today we're going to be starting to talk about the forms that we can put those structural shapes into to generate the gravity framing and the bracing that help us withstand the forces that we can't really assess. And so today we're going to be talking about how those shapes take form in structures. We're going to talk about the tools we use to analyze them. For the most part, you should already have those tools. You should be able to draw a shear and bending moment diagram if I gave you a simply supported beam with loads on it, and you should be able to solve for the internal member forces in a truss system. And over the next 2 lectures, we're going to be talking about how do we come up with the loads, or how do we trace the loads in our structure to those elements to set up the problem that you already know how to solve. How do you get that beam with the loads on it? How do you get a truss with the loads on it? And then over the next few lectures, we're going to talk about the forces that we can't really assess and how we use the NBCC to assess them and apply them to our structure. And then we can use the tools that we're talking about today and Wednesday to analyze the structure under those loads. Okay? So really what I'm talking about today, for the most part, is the middle part here. Everybody knows how to do some basic structural analysis. There are still a few things that you need to understand about how buildings work to set up those problems that you already know how to solve. But this is where we make the loads from the National Building Code of Canada line up with the steel standard for the design of the elements in a building. Okay, so basically today we're going to be talking about the structural analysis techniques that we can use to analyze our structures. And of course, during the labs, we're also going to be looking at the use of STAAD.Pro to do some of this analysis for us as well. But there's no point in using STAAD.Pro until you understand what the answer should be based on hand calculations. So basically what we're talking about today is gravity framing in steel structures. First of all, we're going to actually look at how structures are built. Because if you don't understand how the structures are built, then you don't understand how the loads get transmitted from the floor system down through the foundations. So we're going to look at how steel structures are framed. We're going to look at the different steps of a steel contract, for example. And then we're going to talk about how we trace the loads from a floor, for example. If we had a uniform floor acting, or a uniform load acting on one of these floors, how do we turn those uniform loads into distributed loads on joists and point loads on girders and axial forces in columns? This is a picture of the just this building about halfway through construction. And so it was kind of nice to have a landmark structural steel project being constructed in downtown Fredericton during the summer. It was great to go get some pictures of the structure in action, seeing the steel workers actually put everything together, because I can share that with you in a lecture about gravity framing. In general, this is what somebody like Ocean Steel or Tech Steel or York Steel or other provinces' steel fabricators would be responsible for. Basically everything above the foundations at the top of the grade level on the site to the finished floor level where we have, for example, some steel decking put down on top of the joists. Everything from the top of the foundations to the underside of the concrete floor is something that goes into the steel contract, and that's what the structural engineer would be responsible for designing. Of course, the structural engineer might also be responsible for foundations or for the slabs on the steel deck and for other elements as well. But in general, drawing packages get split up in terms of the subtrades, and so somebody would be responsible for concrete works and foundations, but that would go out as a separate package, and so maybe one engineer is responsible for detailing those, and maybe another engineer is responsible for designing the superstructure and the structural steel framing, and that goes out as a separate drawing package to the steel fabricators. Okay, so they get broken up into separate contracts, and usually the engineer of record would be different for those, just to make sure that they can get everything done in a timely manner, though sometimes the engineer might be responsible for all of the elements in a building. Okay, so basically today, after this, you should be able to identify and describe joists, girders, and columns. So which beams are joists, which are girders, and where are the columns in the steel framing, and how do we arrange them to carry vertical loads down to the foundation. You should also be able to define and calculate tributary areas. Anyone heard of the term tributary area before coming to this course? Anyone from St. John here, like UNBSJ for the first 2 years? Tributary area? Yeah, no? No? Okay, so a new concept for the course, that's fine. I should be able to define and calculate those for joists, girders, and columns. Basically, all the tributary area is how much floor area one element is responsible for supporting, and we'll talk about that today. And then you should be able to draw the effects of a uniformly distributed floor load on a free body diagram of a joist, a girder, or a column. Okay, so that's how do we get the loads acting on those elements, and then you should be able to set up that problem that you already know how to solve based on things that you learned in previous courses. Okay, does anyone have any questions about what these learning objectives mean or why they're important to your success in the course? All right. So before we get into all that stuff, like this isn't a specific learning objective for the course that you understand how steel buildings are put together, but it's important to have that context to do the other things, okay? So this is sort of supporting information. It's interesting if you're interested in the construction, for example, of structures. And so what we're going to be talking about today is from ground zero, how does the steel framing actually get erected on site to form the final structural form? So before I start talking for longer than I need to, I just want everyone to perhaps take a minute, talk to the person next to you if you want to talk to the person next to you, or take a minute by yourself to think about some of these things. If I gave you this picture and said, here are some sticks and here are some floors, how would you go about actually assembling this structure so that you could build it all properly? What would be the sequence? What would the sequence look like? How would you put everything together? And what tools might you need to actually do the installation of those things? So take maybe 30 seconds to a minute, talk with your neighbor, call home if you have a friend at home you want to talk to, and just think about it, and we'll come back and talk about it after. Okay, I think I'm really happy to hear how loud things got. It sounds like there's some good discussion. Whether you're talking about this or not isn't really the point. But I'm curious, anyone who did talk about how you might build something like this, does anyone feel comfortable sharing some of the first steps or any step along the way that you think might be relevant to the process of building this thing? Nobody has a clue, right? I don't think that's true. I heard...
Okay, well, I can explain it in like dumbed down terms because I don't know the actual names of all the stuffs.
Yeah.
But, so I would assume that like those little footy things at the bottom of the beams would go into already like pre-existing foundation piles that are already there. And then from that point, your like I-beams or whatever would be set into that.
Yeah, so either you've seen this before or you thought about it while you saw the slides before, and it doesn't matter which it is. That was pretty much, for the most part, how a steel structure is built. We'll go through those steps and we'll see what it looks like, okay? Generally, the start of the steel construction contract starts once these concrete foundations are in the ground and backfilled. Okay, I don't show the backfill here because I want you to see what the foundations look like. These would be shallow foundations. Maybe you can do shallow foundations on a site, maybe you can't. You'll learn about that in foundation engineering, this term. But in general, the steel contract starts by the time that they've got these concrete footings in place. And basically what the top of these foundations look like once they're backfilled, they'll have the rectangular pier that sits on the footing. And then within those, they're going to have these 4 things called anchor rods that are embedded into the concrete foundation with the reinforcement. And basically, there are typically 4. There might be 6, but there's never fewer than 4 anchor rods poking out of the pier of the footing. And that's where the steel structure starts to be erected from. Okay, so basically, once all these foundations are in place, then they start to crane the columns in place. And so this is the flat plate thing that Ridley was talking about. This is called the base plate. It sits at the base of the foundation. And the base plate will already be welded to a section of the column in the shop prior to being shipped to site. And column by column, a crane will pick it up. It'll put it such that the 4 holes that are pre-drilled in the anchor rod, in the base plate, go over top of the anchor rods. And then usually they'll use something below this base plate to help plumb it and level it. And they might have a surveyor on site to help make sure that the column is plumb and straight before continuing on with the rest of the process. So usually they'll put at least 4 in place, and from there they'll start to crane in and secure some of the beams framing the floor system. Usually there will be some segments of beams going in a long direction, some in the short direction, and then they have to be temporarily braced so that everything stays in place while they're putting this stuff together, because inherently the framing is unstable. And light wind or for any kind of construction loading, they'll temporarily brace it. Maybe they'll tie it back to some other points. But they'll start to tie the columns together with these joists and girders. Now, if you just saw these 4 things, you wouldn't know which was a joist and which was a girder. We'll talk about why one is a girder and one is a joist in a second. But what you'll see is that the ends of the beams get connected to the face of the column with these, we call them simple connections. And what a simple connection does is it just supports the vertical load at the beam at that end. It doesn't provide any rotational restraint because it's not connected to the flanges. We'll talk about that a little bit more later on. But whenever you see a connection that looks like this, it was designed only to support the beam vertically. Basically, what that means is it's designed to resist the shear force that's at the end of that beam. And what it also means is it allows us to treat all of our beams as if they're simply supported, for the most part, as long as they're using these types of connections. The angles are oftentimes either welded or bolted to the beam first. The holes are pre-drilled in the column. And so when they lift this into place, they'll bolt it to the face of the column or to the web on the other side here. Okay, so they'll make a little square connecting the 4 columns together and brace it so that it's stable to continue working on. After that, they'll start to crane in the rest of the beams that support the floor. And so they start to fill in the grid here. In this case, they've got some beams going in the long direction that are connected to the deeper beams in the shorter direction. And this is when we know which beam is called the joist and which one is called the girder. The joists are all of the elements that are connected to the other beam in a perpendicular direction, and the girder is the beam that is responsible for supporting those joists. So essentially the floor is going to run across the joists. The joists are going to be loaded more or less uniformly, and then those loads from the joists are going to be transferred to the girder at the points of the connections along the length of the girder. You can see here, it's a relatively slow process. There's a crane operator and 2 iron workers up here who are responsible for craning the joist into place and setting it in and bolting everything together. And so it's kind of like Legos because it's all fabricated on site so that it fits together with a certain set of plans. But there really aren't that many people who are there doing the work. And you couldn't really have that many more people anyway because you've got 1 crane on site. It takes up a lot of space. It takes a lot of time to operate the crane. And so you're generally not going to be super productive if you can only get 1 crane on site to do this kind of work. Okay, so you basically continue that bay by bay until the first level of framing is more or less completed. And at that point, you start to put in some of the permanent bracing. Okay, so these braces are there for the final form of the structure to make sure it doesn't fall over and to make sure it can withstand forces from wind and earthquakes. And they get connected to the beams and columns using these flat plates, right? So we call that a PL, something by something by something, and that's called a gusset plate, the flat plate thing. Okay, so the gusset plate is usually going to be welded to the column and the base plate down here. It might also be welded to the beams up there. In this case, isn't the best example because there are a couple gusset plates going on in this particular instance, but that's usually how braces would get connected in the field, is they'd have some plates welded to them already, get bolted to some existing gusset plates in the field. After that, they start to lay down the steel deck, and usually they're either puddle welded, which means they take an electrode and they melt the steel down through the top, or they use a high pressure pneumatic nailer, usually by Hilti or something like that, to drive nails down from the steel deck into the tops of the joists. And what that helps to do is, one, it fastens the floor together, and two, it braces the joists. So the joist is only going to bend downwards, and it's also going to help make sure that the floor essentially behaves as if it's one rigid system. All right? So if this was a floor system supported by beams, the steel deck and the concrete on top eventually makes it act as if it's just a rigid plate in space supported by the framing. After that, you go piece by piece. If you've got a taller structure, you're not going to be able to crane a column that's 4 or 5 or 6 stories tall. You're going to have to do them in segments. And so at a certain point, you'll get to the time where you need to install a field splice to connect a new section of column to the old section, and then you continue the process from there until you have the final framing completed. Okay, so the steel contractor is responsible for all of that work from the tops of the foundations until all of this steel is installed with the steel deck on top. After that, they're done, and the concrete folks and other trades come back to finish off their scope of work. Okay? Does anyone have any questions about what that process looks like in general? It's not as important as some of the other stuff in the course, but having that process in mind will certainly help you trace loads down to the structure and be a better engineer when you're designing some of these components. Any questions about that? Great. So what's important for the engineer to do here? How does the engineer communicate this to the fabricator who's responsible for actually building it? Like, what does the engineer use as a tool of communication to tell the contractors what this building should look like in the finished product, do you think? Engineering drawings, right? So even the world is going slowly towards 3D modeling, and 2D drawings are becoming, well, they're still used all the time. But sometimes on projects, they might even deliver a 3D drawing that has everything in it that looks something like this, and then the contractor can go in and actually look at individual components of the model and build in their connections after they receive that. But traditionally, we would communicate some of these things using 2D plans. And today, we're just going to be talking about the gravity framing. And so basically, if you wanted to know what elements were going in this floor system down at the first level, you might look at the first level plan. And essentially what the plan shows us here is which elements are girders. They're the ones that are connected directly to columns and to no other elements. We've got joists that span between the girders. We've got a little arrow here that denotes which way the steel deck is going to be laid on top of the joists. And then we've got some other information about potential openings and column locations and stuff. Okay, so these are the important things for the course for the most part. We've got columns identified. We've got joist sizes identified. We've got some girders identified. And then there's some other secondary structural elements here, like a trimmer joist. You don't have to know what that is, and you don't have to know what a header is either for this course. But just know sometimes, we've got joists and girders, and sometimes there are some other structural arrangements. If you need to make an opening here, for example, if you want to throw a big elevator shaft up through this space, you need to frame a floor opening around that. And you do that by spanning a header to the other joists and then using short joists in between the header and the opposing girder. Some of the other important things for this course are these numbers that are denoted at the ends of the elements. I've called that there the design shear force. What do you think that that's there for? Why would an engineer put a design shear force on a drawing given to the fabricator? Why do they need that information to build the building? I heard something that was right. Well, from the first day of lecture, we talked about the the engineering done by the engineering consultant and the engineering done by the fabricator. The engineering consultant generally does not design the actual connections between the joists and the girders or the girders and the columns. The fabricator does that. And so the fabricator needs to know how strong those connections need to be. And usually the way that we give them that information is we look at our structural analysis results and we find the factored maximum shear force at the end of the beams and the ends of the joists and girders, and we label them on the drawing so that the fabricator knows how strong those connections need to be. One of the things that confused some people last year and I didn't really think about was the column grid line spacings. First of all, the locations of the columns are usually denoted in an east-west and north-south manner. And so usually east-west, they're numbered 1 through the number of columns, and then north-south, they're lettered A through the number of columns. And the spacing is usually denoted something like this if they're equal spacings. It'll say 3 at 7,500. What do you think 3 at 7,500 tells you about column line spacings A through D? Yeah, they're all equal spaces at 7,500, which is 7.5 meters. Remember in this course, whenever you see a number without units, it's usually either like kilograms or millimeters. And so all dimensions are going to be in millimeters. That means there are 3 spaces, each of which are 7.5 meters. Okay? So that would tell you how long your beam is. When you're drawing your free body diagram, this would be 7.5, 7.5, 7.5. And in the other direction, you've got 4 equal spaces at 10.5 meters. Okay, so at the end of the course, you're going to be responsible for producing a sketch or a CAD drawing of a floor plan that looks something like this. We're not going to talk about it in too much more detail than this, but you'll have this slide as a reference for some of the important information that you actually need to include. And primarily that's the joists, where they are, what the size is, what the shear force is, the girders, where they are, what the size is, and their shear forces, and where the columns end up sitting in your structure. Okay? So that tells us a little bit about what the engineer needs to do to communicate the design to the contractor. And once the design is communicated, we've gone through what the contractor is responsible for when it comes to actually building that structure from the top of the foundation to the underside of the concrete floor slabs. Now what's important for the engineer to really understand, even if you don't understand how things together, you have to understand that once they're in their final shape, where do the loads go? And how do we analyze the structure so we figure out what the forces are? What are the bending moments? What are the shear forces? What are the axial loads in some of the elements? Because once you know that, that tells you how strong those elements need to be, and then you can go and say, okay, this column has a factored axial force of 5,000 kilonewtons, and I'm going to go to my steel handbook and we'll look up something that tells me how strong that is. We'll talk about that in lectures 20 to 24 or something like that. This is the first step into figuring out how strong elements need to be, is figuring out for a given set of loads, what are the actual actions, what are the effects of those loads on my structural elements. So moving on with that, we're going to start with tracing the loads from the floor down through the joists into the girders and into the columns. Okay, we build a structure from the columns up to the joists to support the loads from the joists down through the columns. So the first element that's responsible for supporting, for example, somebody standing on the floor is the floor itself, but the next element down is the actual beam. In this case, I'd expect that on the top right-hand corner here, everyone knows how to draw the shear force and bending moment diagrams for a joist. If I told you what W was and what L joist was, I would expect that you calculate the shear force and bending moment. And if you are worried about that, then I expect that you'll practice how to draw the shear and bending moment diagram to get the maximum shear force and maximum bending moment in an element like that. This course is not about drawing shear and bending moment diagrams. It's about, once you have that information, how do we design the elements to carry those forces. But what this course is about is how do we get W? Where does W come from? Well, W comes from the geometry of the framing, and it primarily comes from the actual magnitude of the loads acting on the floor system. And so if you think about this room, for example, the floor has some kind of subfloor. There's probably a concrete slab that sits on a steel deck that sits on some joists. And then there's a bunch of people and desks and furniture. And there's stuff supported from the floor below it, maybe some ducting, some tiles, some lighting. We'll talk about that on Friday this week. But it's essentially a distributed load of sorts. I know I'm standing here. I'm essentially a point load of X 100 pounds sitting on this one point. But if you take that load and average it out over the floor area, we essentially treat it as if it's a uniform load, and we usually use units of kilopascals to talk about stress acting on a floor. It's kind of like when you did soil mechanics, you had equivalent stress, you calculate H times the density to give you a stress acting at that level. We've got a stress or a uniformly distributed load acting over the floor system, and we need to take those loads down through the structural elements. So basically, the first assumption that we need to make here is that the floor is carrying a uniformly distributed load. And the second thing that we need to assume essentially is that the joists are supporting that load proportional to the spacing between them. And what I mean by that is if we divide up these sections of joists using the center-to-center distance between the joists, we essentially assume that the total uniform load that joist is responsible for carrying is the load that acts over that area that's tributary to that joist. And so this is the first introduction to the idea of tributary areas and widths. It's essentially just a floor area that we assume the load in that element is proportional to. And so for joists, we take the tributary width as being the center-to-center distance on either side of the joist, and then we assume that the load supported by that joist is proportional to that area multiplied by the uniform load. Essentially what that means for our statics problem is we take the tributary width for our joist, which is the center-to-center space on either side, and we multiply that by the pressure to get a uniformly distributed load. And if we're using kilopascals and meters for the load and the tributary width respectively, then we'll get a load in kilonewtons per meter. One of the things you'll hear me say in this course a lot is newtons, millimeters, megapascals. And you're going to hear me talk about that a lot when it comes to the design of the actual steel elements. But when we're doing our structural analysis, it's pretty much always kilopascals, kilonewtons, and meters. So kilonewtons, meters, kilopascals. If you do your structural analysis using kilonewtons, meters, and kilopascals, you're going to get shear forces in kilonewtons, moments in kilonewton meters, and they'll be easy enough to translate into newton millimeters when we get to the steel design part of the course. Okay, so structural analysis done in newtons, millimeters, and kilopascals. The actual mechanics of materials done using newtons, millimeters, and megapascals, and then we'll convert one set of units to the other when we actually decide and start comparing the capacity to the loads, for example. Okay, so this is a problem you should be able to solve. The only thing that's new is if I give you a load in kilopascals, you should be able to calculate W and start that statics problem from what you learned in 1023. Does anyone have any questions about what that tributary width means and why that's an important assumption to start us down the path of calculating the loads and the elements in our structure? So what's important for our joist here is we need to know what the reactions are. We'll see why that's important in a minute. We need to know what the shear and bending moment diagrams are like, for example. If we start looking at the next piece of the puzzle, some of those joists are supported by the columns, but some of them are supported by the perpendicular beams, which are the girders. And basically, if we look at the middle girder here on column line 2 between B and C, that's shaded with the slightly darker green region here. It's in red. So this girder here is what we're looking at. And if we look at that area, we can see that that girder is responsible for supporting 3 joists on this side and 3 joists on this side. And if we know that the joist is going to be supported with a certain reaction force, then I've just labeled that reaction for the joist, then we basically know that that reaction needs to be provided by the girder. So the girder needs to be strong enough to provide a reaction force equal to the reaction on the joist. And from Newton's whatever law, first, second, or third, could care less, we know that every action has an equal and opposite reaction. And so that reaction force from the joist is the action acting on one of the girders. Okay, so that force that's provided by the girder on one side is the load that is acting on the girder. So we've got a joist A on one side, loading the girder with a reaction force. We've got joist B on the other side, loading the girder with a reaction force. And at all the other locations, we've got C, D, E, and F, loading the girder with that reaction force. Okay, so we've got reactions at the locations of the joists. Those are the loads that are going to be acting on my girders. And once you have that problem, now you can do your shear and bending moment diagrams like you would have learned to do in 1023 and 2023. Okay, so we're just looking at how the loads come from the joist down through into the girders. And one of the things that's interesting about that is if you actually look at the tributary areas associated with each of these, we've got a tributary area for joist A, one for joist B, C, D, E, and F. Half of the load from the joist goes to one girder and half goes to the other. And so if you draw an area that's proportional to the reaction in each joist, so this slightly darker green area here would correspond to the load at the ends of the joists, and we look at the contribution of the area from all the joists to the girder, what we get is a slightly darker area here, and that's going to be the tributary area for our girder. That is the area of floor that the girder is responsible for supporting. Okay, so when you're calculating tributary areas for the girder, basically you can just look at the tributary areas for the joist, multiply those by the number of joists and divide it by 2, and you're going to get the tributary area for that girder. Now, we don't really use the tributary area for our girder much to calculate loads or shear forces or moments, but we will look at the tributary area for our girders at some point when we start talking about the dead and live loads acting on our structure. So it is important that you understand this concept of tributary area. Basically, if you look at the sum of the joists acting in this area, you can sum up the tributary areas from your joist and divide it by 2 as long as there's a regular spacing in your structure, and you'll get the tributary area for your girder. Some of our joists are directly supported by columns instead. Okay, so this little piece is going to go to the column, this little piece is going to go to the other column, and those joists are going to have reaction forces that are directly transferred into the columns. And if we look at the other elements supported by the column, in addition to those 2 blue joists, we're also going to have a couple of girders. Right, so if we're looking at this column here, B2, there's going to be a reaction from the joist on either side, and there's going to be a reaction from the girder on either side, and the column is responsible for, at each floor level, supporting that additional amount of load from each of those elements. So if we do the same thing that we did for the girder, we draw out the tributary areas for the girder on one side. This red is the tributary area for girder A. Half of the load goes to this column, but this half goes to the column here. And same for girder B. We've got half of the tributary area here in red. That's proportional to the reaction force in girder B. And then we've got half the tributary area for the other 2 joists framing into it. And if we look at those areas now, that's the floor area at this particular level that this column is responsible for supporting. Okay, it's responsible for supporting the reactions for the 2 girders and the reactions for the 2 joists. And if you look at the tributary area for those 4 elements and the force that's going into that column, now we can draw a rectangle that represents the amount of floor space that that column is directly responsible for supporting. Okay, so we can trace it kind of back to the additional compression in a column from a floor is going to come from the 2 joists and the 2 girders. And if we wanted to calculate the tributary area, we can just look at the length from 1 to 3, which is this, the length from A to C, which is this, and if we take those 2, multiply them together and take it divided by 4, then we get the tributary area at that floor that that column is responsible for supporting. Okay, so we've essentially gone through 3 important tributary areas. There's one for the joist. We don't use it for much except for calculating the tributary areas for the girder, but we do use the tributary width to get the load on the joist. We also use the tributary area to demonstrate how much load or how much floor area the girder is responsible for carrying, and we'll come back to that later on, and we don't use it any further for our structural analysis, except for when we're talking about the tributary area about our columns. But we don't even need to know what the tributary area for our joist or our girder is to actually calculate the tributary area for our columns. We just need to know what the column spacings are. Okay, so we don't need to continue that information through except for our girders. Does anyone have any questions or concerns about the concept of what tributary area means and how it can help us take loads down through our structure, through our joist girders to our columns? It's a pretty simple concept, but if you don't get it, you won't get anything else right. Okay. So if you're confident in it, that's great. If you're not super confident in it, you're going to need to spend a little bit of time with it. And the last thing that tends to confuse some folks the first time they see it is joists and girders only support one floor. The joist supports the floor, the girder supports those joists. They don't carry any other loads. But the column goes all the way up through the height of the building, and so they're actually responsible for carrying several floors. right? The bottom column is responsible for supporting the first floor, second floor, third floor, and the roof. And so in this case, yeah, the tributary area for one level is equal to this, and that would tell you, for example, the force in that column. But if you wanted to get the force down here, that's responsible for carrying 2 of the floors. And the third column down is responsible for carrying 3 floors, and the final column at the base is responsible for carrying 4 floors. And so if you're designing the columns, which one's going to be the most heavily loaded, and which one's going to need the strongest structural element, do you think? I hear some lips moving, and I've heard bottom, or I've seen bottom. The bottom column is going to be the most heavily loaded. It supports the most floors. The top column is going to be the least heavily loaded. It supports 1 floor. Okay? So we're going to get some opportunities to practice these concepts, particularly through the assignments and on the quizzes. The quizzes focus a lot on tributary area and setting up the statics problems for this lecture. But the last thing I want to do today is go through a quick example on how you might apply some of the tributary area concepts to get some of the loads that are acting on the structure. Okay, so in this example, we're working with this floor plan, okay, numbered 1 through 5, A through D. We're going to look at this joist, we're going to look at this girder, and if we've got time, we're going to look at column B3 here, okay, and see what the load in the structure might look like for those elements. This floor is carrying a uniformly distributed load of 7.2 kPa. That's just the number I pulled out of thin air. We'll talk about how we can figure out what that number should be over the next couple of weeks. Quantifying this comes from the National Building Code of Canada. Today we're just looking at a load of 7.2 to practice some of these concepts. First thing we're going to do is figure out what the tributary width of the joist is, and we're going to use that width with the load to set up the simple beam bending problem so that you can calculate the shear force and bending moment in that joist. Okay, so for the first part, we're just going to look at the joist. Does anyone have any questions about what our objective is here with this joist and why we're looking at this one? Okay, so we're going to start by looking at this blue joist, and the first thing that we need to do is figure out the load. We've already been given the load, so that's been taken care of. The other thing that we need, if we come back to our slide here, we've got load P. That's what P means here. That's the uniformly distributed load on the floor. The other thing we need is the tributary width of that joist. Okay, so the tributary width is the center to center distance between the joists and the building. So if we're looking at that one, that's this area here. How would we calculate that from the information given on our floor plan? If we were to look at that, we would see, okay, the distance between column line B and C is 7.5 meters. And then we're just going to count the spaces between joists. We've got 1, 2, 3, 4 spaces between the joists. And so if the joist spacing is 7,500 divided by 4, the tributary width for that joist is going to be 7.5 meters divided by 4, which is 1.875 meters. Okay, so that's the tributary width for that joist. That's the area of floor that the load in that joist is proportional to. And so if we go ahead and we try and set up what that problem looks like, we're going to have a simply supported beam. And just remind everyone, the reason we're using a simply supported beam is because we're dealing with simple framing where the connections at the ends of the building don't transfer any moment. And so for connections that don't transfer moment, they only transfer shear, we can model that simply as a simply supported beam. Now, this is not exactly right, but it's close enough. It's a model that's going to give us the information that we need to design our structures to be safe. This is going to be the load W, which is equal to the uniform pressure multiplied by TW for the joist. So we've got a 7.5 meter long joist, and W is going to be equal to the pressure, which is 7.2 kPa. Again, we'll talk in later lectures about how we calculate that pressure. And we're going to multiply that by the tributary width for the joist, which is 1.875 meters. And so if we do that, we get 7.2 times 1.875. And that's going to give us a uniformly distributed load of 13.5. What are the units? Kilonewtons per meter. Distributed loads are always a force per length. In this course, we do the structural analysis with kPa, kilonewtons, and meters. So if you multiply kPa by meters, you get kilonewtons per meter. Okay, so basically what you have is you have a 7.5 meter long joist that's simply supported with a uniformly distributed load of 13.5 kilonewtons per meter. And now you've got the problem that you talked about since first year of civil engineering. Question?
Could you explain how you got 7.5 meter for the length of the joist?
Yeah, you're right. That shouldn't be that one. I skipped a step here. The joist is actually supposed to be 10.5 meters. So thank you for bringing that up. It's easy to look at the numbers. I looked at 7,500 to calculate the tributary width for the joist, and so that was incorrect. That should actually be the 10.5 meters for the other direction. 10.5 meters. All right, so that was a good question. The joist is actually, going from 2 to 3, and the space in between 2 and 3 is 10.5 meters. So now that you're doing the problem, you should be able to do this one. Thanks for bringing that up. Any other questions about that particular exercise? Okay. The next thing we want to look at is the girder that's blue. Okay, I'll get rid of some of this other stuff. So we're going to look at this blue girder now. Sorry, red girder. The joist is blue. And the first thing we need to know about the girder, first of all, I should get the length right. The girder is going to be 7.5 meters long. But now I need to figure out, okay, which joists is this girder supporting? And what are the point loads that the joists will be placing on my girder? What are those going to be? And once I have that information, I can set up my statics problem and do the shear and bending moment diagrams. How many joists is this girder supporting in total?
6.
We've got 6. We've got the ones from 2 to 3 and the ones from 3 to 4. 1, 2, 3, 4, 5, 6. And when we look at the reactions coming from those joists, we know that one reaction is going to be on the girder over here. The other reaction is going to be on the girder over here. And so the point load here is going to be the load from half of each joist. And so if we come back to how it was described on a previous slide here, maybe this one, we'll see that we're going to have 3 point loads from 6 joists. Right, so we're going to have 1, 2, 3, 4, 5, 6 different loads coming in at 3 locations. And we can calculate those loads based on the tributary area of the joist framing into it. Now, if we look at this one, we can split it up into 6 individual things, or we can solve the reaction acting on the joist and multiply it by 2 and put it on here. So we could say, okay, from our statics problem for the joist, what's the reaction? And then we can, because the joists are the same on all sides, multiply that by 2 at each location. And so that's what we'll do for now. So we actually need to continue our problem slightly for our joist here. We need to figure out at each location what the reaction force is going to be at the ends of our joists. And to shake the cobwebs off, everyone from statics, if we've got our joist on one side, we can take moments about a certain side, or we can identify that the beam is symmetrically loaded and symmetrically supported, and immediately identify that the reaction in this joist is going to be equal to the total load acting downwards on this beam, which is going to be 13.5 kilonewtons per meter times the length, times the 10.5 meters, divided by 2. And if we do that, we've got 13.5 times 10.5 divided by 2. And that's going to give us a reaction force for that joist of 70, and I'll round up to 0.9 kilonewtons. Pressures in kPa, distributed loads in kilonewtons per meter, loads in kilonewtons. Okay, so I've got the reaction from my joist, and now I can set that up over here to set up the problem for my girder. I've got a space, the length of my girder here is 7.5 meters long. I've got 3 joists, so this is split up into 1.875 meter increments. And then I've got 70.9 times 2 in 3 locations. And so if I look at that particular load and I say, okay, well, I've got the reaction from the joist, I've got that at 3 locations, and I've got 2 at each location, the total load at each location is going to be 141.75 kilonewtons. Okay, and that's this total downward load, 1, 2, 3. And now you've got your point load P at 3 locations on a beam of length 7.5 meters. And now you've got a statics problem that you've been learning how to solve since the first year of civil engineering. Okay, does anyone have any questions about how we use the problem from the joist to set up the problem for the girder, and how we could continue with this particular problem to figure out what's going on with the internal forces in that element? Good. So the last thing that we want to do, time pending, and maybe we'll just set up the problem briefly, is we want to figure out what the total compression on column B3 would be. And what I mean is, what is the total compression at the bottom from all 4 floors carried if we've got a uniformly distributed load and we've got a column at this particular location. Okay, so if we go back to this slide, we can see, okay, this is pretty similar. We've got column B2, it's over here. B3 is going to have a similar tributary area. We can calculate the tributary area for that column, and we can figure out how much load the 7.2 kPa pressure adds to the column at each floor level. We're going to have 7.2 times the tributary area at the top, at the 3rd floor, at the 2nd floor, and at the 1st floor, and the column has to support all of that load. Okay? So if we start with the columns here, or maybe we'll start with the floor plan, and we look at the column B3, we're going to look at the distance between each of these. This is my tributary area here. And if you do it based on the equation that I gave you back here, we're going to look at a quarter of the distance between 1 and 3 and A and C, or in our case, the distance between 2 and 4 and A and C. Okay, so the distance from 2 to 4 is 21 meters, and the distance from A to B is 15 meters. You can also look at it as the distance between the 2 columns if you've got similar column spacings, but this is the more general approach if the column spacings actually varied slightly. Okay, so the tributary area for one floor, and I usually just denote that tributary I, is going to be equal to 21 meters times 15 meters divided by 4. So if we do that math, we get 21 times 15 over 4, and we get 78.75 meters squared. And if we look at how many floors we need to support, we can see here for a 4-story building, if the load's all the same, we've got 4 floors. And so we can multiply the tributary area by 4 to get the total area supported by the column. So the total tributary area for that column B3 is going to be equal to 4 times the tributary area for the individual floors. And so I can just get rid of the divide by 4, and I get 315 meters squared. Now, if all 4 floors carry the same pressure, we can say the total compression acting in that column is going to be equal to the tributary area for that column multiplied by the pressure on each floor. That's going to be 315 meters squared multiplied by the 7.2 kPa. And if we do that, the total acting on that floor area, 7.2 times 315, is 2,268 kilonewtons. Okay? So just to recap that quickly before closing things off, we looked at each individual element here, the joist, the girder, and the column. We used the concept of tributary area to set up the statics problems for those particular elements. And I want to ask a couple questions here before we part here. We did the blue joist here. What's going to change for any other particular joist here? Is anything going to change for most of your interior joists from that problem? If the load's the same everywhere? All of these joists, they have the same spacing and they have the same load. So the joist loads and the problem, if you solve the blue one, you're solving essentially all of the other joists, except perhaps these 3 shorter ones down here, and except perhaps the ones on the outside of the building. And so once you know the loads on one joist, you know the loads on almost all of your joists. How about the girders? What's going to change for your girders? Is the problem we set up for the red girder going to change substantially for the rest? This girder is going to be the same as this one, the same as this one, and this one. Now, the joists framing into this girder are slightly different, so you'd have to do a different problem here. And if you're looking at this girder on the outside, they've only got the joists on one side framing in, so the loading would be half in that case. The last thing I want to ask, what would be different for column A3 compared to column B3? What do you think is different for that column? Yeah, it has half the tributary area because it's only loaded on one side. And so we've got two joists and this girder framing in. The tributary area for outside columns is half for interior. And what do you think A1 would be? A quarter, right? So if you know the tributary area for one column, you know the tributary areas for the rest of them. It might change for these columns down here because this opening changes things, but we're not going to be talking about that in this class. Okay, so now you should be able to identify which elements are joist girders and columns. If you can't, review the lecture slides and watch the video. And how they're arranged to carry loads down the foundation. Should be able to define and calculate the tributary areas for those particular elements when they're simple framing and it's relatively uniformly distributed in terms of the spacings and the load. And draw those effects of the uniformly distributed floor load on a free body diagram of the joist of the girder. And I didn't really draw it for the column, but you would just draw the loads from each floor at each location, and you could draw what's called an axial force diagram, which is the change in the load from top to bottom. Okay? Does anyone have any questions about any of those concepts before we wrap up for the morning? Yeah?
On the example, there's like those little dotted areas on the girder. What does that mean?
The dotted areas? Oh, sorry. So we'll talk about that next day. These aren't girders. This is going to help us identify and plan where the bracing is in the building. Okay, we'll identify that. I think it's labeled on slide, whatever the slide was. Let's see. Back to this one. So it should be labeled, this location of bracing between floors and columns. So if you see the dashed line and you're wondering what's going on there, we'll talk about that on Wednesday. Any other questions? Great. See everybody on Wednesday.